Two charges attract each other with a force F. One charge is doubled, the other charge is tripled, and the distance between them is reduced to 1/4 its original value. What is the new force value now? Well, we use the known equation for the force between two charges, F equal to K Q1 Q2 over R squared. Now, what happens is the first charge Q1 is doubled, it becomes 2Q1. The second charge Q2 is tripled, it becomes 3Q2. And the distance between them R is reduced to 1/4 of the original value. So R now becomes 1/4 of R. And now the new force F prime is therefore K times 2Q1 3Q2 over 1/4 R all squared. And look at those numbers. This 1/4 squared becomes 1 over 16, and that 16 is on the denominator. It will go up, combines with this. 16 times 2 is 32, times 3 is 96. So the numbers will multiply to become 96. And what are the left quantities? K, Q1, Q2 over R squared, and that is your original F value. So the new force F prime is 96F. Second question. If the mass of a proton is 1.67 times negative 27 kilogram, how many times is the electrostatic force between the two protons compared to the gravitational force between them? The value of the gravitational constant and the value of the electron charge is given, and also we know the mass of the proton. So we can use these first to find the gravitational force between the two protons. Gravitational force equal to gravitational constant times mass of protons multiplied by mass of protons divided by R squared. And using those numbers and simplifying, we get 1.86 times 10 to the negative 64 Newton. You can see how weak the gravitational force between two protons is. It's a very, very small, insignificantly small number. But can we simply throw it away? No. All right, what is the electrostatic force between the two protons? It is K times, where K is the Coulomb's constant, charge on the first proton times the charge on the second proton divided by R squared. And now put in those values, K, and the charge is, that we know, divided by R squared. That simplifies to 2.3 times 10 to the negative 28 Newton. Now, how many times is the electrostatic force greater than the gravitational force? What is Fe over Fg? That will be 2.3 times 10 to the negative 28 divided by 1.86 times 10 to the negative 64 Newton. That is 1.24 times 10 to the 36. You can see the electrostatic force is so much bigger than the gravitational force. It is 1.24 times 10 to the 36 times greater. All right, the third one. An electric field is created by two parallel plates. At which of the following points is the electric field the strongest? Well, it's a very simple question. The electric field between the two parallel plates, the lines of force are parallel. What does that mean? It means the field is a constant. The field value at any point is the same. In other words, the field at A equal to the field at B equal to field at C equal to field at D. Next one. A uniform electric field is created by two parallel plates separated by a distance of 0.04 meter. What is the magnitude of the electric field established between the two plates? Well, look at the unit of the electric field is volt per meter. The unit actually helps you to remember the relation between electric field and electric potential. Volt per meter. Electric field is negative dV over dr. Now what is dV, the change in potential? Is negative 40 volts minus 40 volts. That will be 80 volts. That is the change in potential. And dr is 0.04 meter. Therefore, electric field is negative dV over dr. That is 2000 volts per meter. Next one. An electric field due to a positive charge is represented by the diagram below. Which of the following points has the higher potential? Now remember, the potential at a point is electric potential at a point is a measure of the work done to bring a unit positive charge from infinity to that point. That means as the point gets closer and closer to the positive charge, the work done is becoming greater and greater. So a point closer to the positive charge has a greater potential than a point far away from it. So which of these points is the closest? Is A. Another one. An electric field due to a positive charge is represented by this diagram. Again, the same diagram. Between which of the following 2 points does the electric field do zero work on a moving charge? Well, one thing that you need to understand here, these circles, what do they represent, these blue circles? They are actually equipotential lines. What does that mean? It means at any point on a single circle, the potential values are all the same. And one of the things that you must understand about equipotential surface is that the electric field lines are at right angles to the equipotential lines. Did you see that? All electric field lines are at right angles to the equipotential lines. So, how do we answer this question now? Between which of the following 2 points does the electric field does no work? Well, if you can find 2 points on the same equipotential line to move a positive charge or move a charge from one point on the equipotential line to another point, you do no work because there is no potential difference. Can you find 2 points on the same equipotential line here? Well, if you notice C is the point on this equipotential circle and D also is on the same circle. Therefore, C and D are at the same potential to move a positive charge from C to D. You don't need to do any work because the potentials are the same. Next one. In the diagram below, The electric potential at a point A is V. The potential here is V. What is the electric potential at the point V? But remember, we know the potential at a point is, well, K, Q over R. In other words, the electric potential is inversely proportional to the distance. So if this V equal to KQ over R, what will be the potential V prime at B? It will be KQ over, if this is R, what is this? That will be 4R, is that right? That's correct. So that will be 4R, and that will be 1/4 of KQ over R. And what does KQ over R represent? It's the potential at A. Therefore, the potential at B is 1/4 of the potential at A. So that's equal to 1/4 of V. All right, let's move on. A non-uniform electric field is represented by the equipotential lines. What is the direction of the electric field at point A? Well, if you remember what we discussed in the last slide, what is an equipotential line or equipotential surface? An equipotential line is a line along which potentials at all points are the same. And also, the electric field at any point on the equipotential surface is at right angles. Therefore, the electric field at A will be somewhere that direction. In other words, it is this. Now, can you plot the electric field in this region? If you now look at A, and if you look at here, if a line starts that way, it has to go that way. Why? Because it has to be at right angles to the equipotential line. It will go at right angles there, at right angles there, and maybe that way. So that is one electric field line. Another will go like that. One goes like that. That's perpendicular at every point. Is that right? And another one. So what is this electric field? What kind of system creates this electric field? It'll be a positive charge here and a negative charge there, and that is responsible for a field like this. And you can see how equipotential lines exist in a field like that. All right, let's move on. Another one using the same diagram. A non-uniform electric field is represented by equipotential lines. How much work is done by the electric field when a positive charge of magnitude 1 microcoulomb moves from point A to point E? Moves from point A to point E there. In other words, from a point of potential 20 volts to another point of potential negative 20 volts. What is the potential difference dV equal to? Equal to 20 minus negative 20 equal to 40 volts. Here we need only take the magnitude, so don't worry about how we subtract the 20 minus negative 20 or negative 20 minus 20. So the magnitude of the change in potential is 40 volts. That's right. What does that mean? What is a volt? A volt is joules per coulomb. In other words, It means the amount of work that needs to be done to move one coulomb of charge from A to E is 40 volts. That's the meaning. The potential difference is 40 volts. Therefore, what is the work done when 1 microcoulomb of charge moves from A to E? So, when 1 coulomb of charge, for 1 coulomb of charge, the work done is 40 volts, means 40 joules per coulomb. Therefore, the work done when you move 1 microcoulomb, so W for 1 microcoulomb is work done for 1 coulomb multiplied by the amount of charge, that is 1 microcoulomb is 10 to the negative 6 coulomb. So that is 40 joules per coulomb times 10 to the power of negative 6 coulombs. That will be 40 times 10 to the negative 6 joules, and that is 40 microjoules. Okay, next one, we've got a third question based on that. A non-uniform electric field, again, is represented by the diagram. A positive charge with a magnitude 1 microcoulomb moves in the following path. What path does it go? A to B to C to D to E and back to A. How much work is done by the electric field? Think about it for a moment. What is it analogous to in gravitational field? If I raise an object, what is the work done by force of gravity? The work done by force of gravity is negative mgh. Now, when that object falls back here, what is the work done by the force of gravity? Remember, not work done by the external force, work done by the force of gravity. It will be mgh. What is the total work done? The total work done is the sum of the two, which will be 0. Now, what do we call such a field? Now, this is the gravitational field. Such a field is called a conservative field. And what is the characteristic of a conservative field? In a conservative field, the work done to move an object in a closed path is 0. So in a gravitational field, the work done to move an object of mass m in a closed path is 0. In the same way, an electric field is a conservative field. Therefore, work done by a positive charge to move in a closed path is 0. So the work done to move 1 microcoulomb from A to B to C to D to E and back to A is 0. That concept is very important. Next, what is the net enclosed charge in the shown cube if the electric field is given by the expression E equal to 2x minus 1i plus 4j? So the electric field has an x component and a y component. Now remember, what is the principle we are going to use here? The principle we are going to use here is the net flux leaving a surface, phi net, equal to the amount of charge enclosed in that space divided by epsilon 0. This is the Gauss's law. So we need to find the net flux in here. How? What is net flux? Net flux is the flux crossing a given area is E multiplied by the area of cross-section. So, first of all, let's take the left face of the cube, that face. Now, what is the electric field there? What is the value of x there? X equal to 0. So when x equal to 0, the electric field is 2 multiplied by -1. So the electric field on the left, I'm going to call it E left, equal to -2I Tesla. That's the electric field that way. All right. Now, what is the flux leaving that left surface? The flux leaving that surface will be that field E multiplied by that area A. What is that area? The cube has of side 2 meter, let's say. So that area is 4 square meter. Therefore, phi net is -2 Tesla multiplied by 4 meters squared. That will be -8 Tesla meter squared. Now, can you find in a similar way the flux leaving the right face of the cube, that face? Now, what is the electric field there? The electric field there is, what is the x value? X equal to 2. Why? Because the length of the side of the cube is 2. When x equal to 2, you have 2 minus 1 is 1, and 2 times 1 is 1. Therefore, E leaving the right phase is 2I Tesla. Remember, we are only taking the x part here, not the y part now. And therefore, what is the net flux leaving the right face of the cube? It will be 2 Tesla multiplied by, again, the area is 4 meters squared. That will be 8 Tesla meter squared. Now, we finished with the x direction. What is the flux leaving the y direction? Well, if you look at the equation, the electric field is a constant in the y direction. It doesn't depend on the value of y. That means if a field is entering here, the same field will leave there. So what does that mean? In the y direction, the phi y net equal to 0. The amount of flux entering is equal to the amount of flux leaving. So the net flux entering or leaving in the y direction is 0. What is the net flux leaving in the x direction? The net flux leaving to the left is 8 Tesla meter squared. Leaving to the right is 8 Tesla meter squared. Therefore, net flux in the x direction leaving the cube is 16 Tesla meter squared. That is the net flux leaving that surface. And there is no flux leaving in the y direction. And we now go to the law, which says phi net equal to Q over epsilon naught. Our phi net is 16 Tesla meter squared equal to Q divided by epsilon naught. Therefore, what is Q equal to? Q equal to 16 epsilon naught coulombs. That's right. So the amount of charge in the cube is 16 epsilon naught coulombs. Now, some of these questions are good for thinking and understanding these concepts. In fact, I have taken these from some of the past exam papers from University of Florida and MIT. Next question. The figure indicates an electric field directed only in the y direction, passing through a cube with the length of the arrows indicating the magnitude of the field at the bottom and the top faces. What can be concluded about the net charge contained within the cube? Well, remember we said Gauss's law is phi net equal to Q inside divided by epsilon naught. Now, if we have a surface here, if there is a net flux leaving the surface, what kind of charge is inside? The net charge inside will be positive. On the other hand, if you have a surface with the net flux is entering, that means the net charge inside is negative. All right, can you use that to answer this question? If you notice the length of the field arrow, the length of the field arrow entering is smaller than the length of the arrow leaving. What does that mean? It means there is a net flux leaving the cube. Now, if there is a net flux leaving the cube, what is the type of charge inside the cube? The charge inside the cube must be positive. Right. Okay. Next one, and I think we will make this the last one. Suppose the electric potential is Vxyz is ax y squared z cube, where a is a constant. What is the z component of the electric field? Now remember we said electric field is the derivative, the negative derivative of the potential. But here the question is, the potential varies in the x direction, in the y direction, and in the z direction. Therefore, we need to take the partial derivative. So we say electric field in the z direction is the derivative of the potential function in the z direction, negative del v over del z. Now, when you want to take the derivative in the z direction, we need to treat the terms in the other direction are all constant. So ax y squared is constant. So what is del v over del z equal to? Will be ax y squared times the derivative of z cube with respect to z will be 3z squared. And of course, the electric field Z will be negative del V by del Z. So that will be negative AXY squared times 3Z squared. I think that will be it. Is that right? All right.